Welcome to our ECE 106 design project. Enjoy! So we've decided to apply capacitors in order to create a sensor that can detect the amount of pulling force applied to the device. We will use circular parallel plates in order to reduce the fringe fields caused by the sharp edges of square plates, and we will use a number of springs around their circumference to convert the known separation of the plates into a measurable pulling force. As we pull on one of the plates, their separation will increase, which in turn will decrease the capacitance. We can measure this change in capacitance with the circuit we will highlight later in our presentation, and from this we can calculate the force that is being applied. So this is a cross-sectional diagram of our design. As you can see, we have our parallel plates at the top and bottom, as well as a section of insulating material on the outside of the plates. Here we can see two of the springs that hold the plates together, along with the insulating stopper that ensures the plates have a minimum separation distance. Attached to the bottom plate is another set of insulating stoppers that set the min distance of the bottom plate can be from the device's enclosure. Now here's our design from an isometric point of view. This drawing leaves out the insulating stoppers in order to show the rest of the design more clearly, but we can see in orange that we have our bottom circular plate, and in green is the ring of insulating material that holds the springs together. Earlier in the design process, we only had two springs holding the plates together on opposite sides of the circle, but we realized that the average spring constant was much too high in that scenario, so we vouched to go with a number of evenly spaced springs on the circumference of the plates in order to reduce the average spring constant of each spring. Now I'll cover the technical parameters of our design. These parameters were chosen in order to measure somewhere in the range of 100 newtons, but this of course could be changed depending on the desired application. The radius of the circular plates is 2.5 centimeters, and their minimum separation, which is the height of the internal stoppers, is 0.25 millimeters. The maximum separation of the plates is 1.25 millimeters, which was chosen to be at least 20 times smaller than the radius of our plates. This ratio was chosen to reduce the effects of fringe fields, which leads to more accurate results. Our overall spring constant is 100,000 newtons per meter, but this is the spring constant of all the device's springs added together. This means that the individual spring constant of each spring will be 100,000 divided by the number of springs. Lastly is our Arduino sampling rate. We are using an Arduino Uno whose ATmega 328P chip has a sampling rate of 9600 Hz. In order to complete our calculations, we had to make some assumptions about our design. Firstly, since fringe fields have already been minimized from using a circular plate capacitor and implementing a 20:1 ratio of radius to separation, we will ignore any remaining fringe fields. Additionally, we will assume that the air between our plates has a dielectric constant of 1. Our springs will be assumed to be perfect springs, and we will assume that the applied force to the device will be parallel to the springs always.
We know from our studies on capacitance that the capacitance of a parallel plate capacitor is given by C equals the cross-sectional area of the plates times epsilon r times epsilon naught all over the separation between the plates. In our case, the separation between the plates is split into two parts. There's capital D, which represents the separation of the plates when the springs are in the unstretched position, and there is lowercase d, which represents the extra separation created by stretching the springs. Using Hooke's law, we know that the force applied is equal to the spring constant times the displacement of the spring, and by solving for d, we can substitute that into the capacitance equation, and we end up with an equation for the overall capacitance of our system as a function of the force applied. And that is C equals to A times epsilon r times epsilon naught all over d plus f over k. Here is a graph for the capacitance function that we derived in the previous slide. Recall that the capacitance as a function of force applied is given by C is equal to A times epsilon r times epsilon naught all over capital D plus f over k. And we can see that this graph clearly matches what our equation is predicting. As the value of the applied force increases, the value in the denominator of our function also increases, which causes the overall capacitance to decrease. In other words, we can say that the capacitance is inversely proportional to the force applied. This makes sense intuitively as well, because as we increase the force applied, the springs will stretch, which in turn causes the distance between the parallel plates to increase, which in turn causes the capacitance of the system to decrease. In order to optimize the capacitance for increased sensitivity, we start out by taking the derivative of the capacitance function with respect to the force applied. This will give us our sensitivity equation. Thus, the sensitivity equation is given as -a times epsilon naught over k times d plus f over k squared. Looking at our sensitivity function, specifically the numerator, we can see that in order to maximize the rate of change, we need to increase the area of the parallel plates. Looking at the denominator, we see that in order to maximize the rate of change, we need to decrease the spring constant and decrease the base separation, capital D. Here is a graph for the sensitivity function that we derived in the previous slide. We can see that the sensitivity function is always negative, which means that no matter what the force applied is, the capacitance will always be decreasing. But we can see that for lower values of applied force, the capacitance is decreasing faster than for higher values of applied force. Again, as we determined in the previous slide, if we want the capacitance to start decreasing faster, we need to increase the surface area of the plates, reduce the base separation distance between the plates, and reduce the spring constant. Here is a circuit that we will be using to measure capacitance. Essentially, it's a very simple RC circuit. We're going to be connecting resistor R1 to 5 volts from the Arduino, which will allow us to charge the capacitor. Then we will be connecting resistor R2 with the value of 220 ohms to the Arduino as well, which will allow us to discharge the capacitor. We know that since this is a step response, the value of the voltage across the capacitor as a function of time will be given by 5 minus 5e to the exponent minus t over R1 times c, where t is the time in seconds. Essentially what we're going to be doing is measuring the value of the capacitance using the time constant. Now the time constant is equal to the amount of time required for the voltage across the capacitor to equal 63% of the input voltage. Since in this case the input voltage is 5 volts, that would be the amount of time required for the capacitor to reach a voltage of 3.15 volts. Now we're going to program the Arduino to find the time constant. The way it's going to do that is by measuring the amount of time it takes for the voltage across the capacitor to reach 3.15 volts. Then we'll discharge the capacitor and repeat the cycle. Using the fact that the time constant is equal to the resistance times the capacitance, all we have to do is simply divide the measured time constant by the value of R1, and that will yield the capacitance of the capacitor. In order to determine the value of the resistance R1, shown in the schematic on the previous slide, we must first determine the minimum capacitance that our setup could produce. This capacitance will be produced when the plates are at their largest separation. We know that the plates have a radius of 2.5 centimeters, and that at their largest separation, the plates will be 1.25 millimeters apart. Using these facts, we can find that the minimum capacitance for our setup is 13.91 picofarads. Now we need to ensure that the time constant for charging the capacitor is larger than the Arduino sampling rate, because otherwise the Arduino might not be able to accurately measure how long it takes for the capacitor to charge to 63%. To be safe, we determine a value for this resistance such that the time constant is at least 4 times the sampling rate of the Arduino, which is 9600 Hz. Setting up the time constant equation and solving for R, we find that we will need a 30 megaohm resistor in order to ensure that the Arduino is capable of accurately measuring the time constant. Thus, the value of R1 from the previous slide will need to be 30 megaohms.
So we start with our design constant set at the beginning, along with the variables start time, elapsed time, picofarads, and force, which the program will calculate. So first we set our charge pin, pin 13 in this case, to 5 volts, and we take note of the current time in the variable start time. The while loop continuously reads our analog pin, which is monitoring the voltage of the capacitor, and when the voltage on the capacitor reaches 63% of the 5 volt input voltage, we stop the timer, and then we can calculate the elapsed time that it took for the capacitor to reach that 63%. So with this, we know our time constant, and we can go ahead and calculate the capacitance in picofarads with our known resistor value. With our capacitance, we can calculate force with the equation that was highlighted in previous slides. And then to prepare for the next loop, we set both the charge and discharge pins to 0 volts and wait until the capacitor is fully drained, and then the program repeats.
Next, we'd like to go over the overall sensitivity of our circuit. The overall sensitivity would be how sensitive our circuit would be with respect to our detectant, which in this case would be the amount of pulling force applied to the apparatus. In other words, we'd like to determine the minimum amount of force that our circuit can detect. Note that from earlier, we've already obtained the equation for the change in capacitance with respect to the force that we are applying. In addition, we know that the time constant for our capacitor, tau, will be the resistive value that our circuit sees multiplied by the capacitor value itself. With these two in mind, we will relate the time constant to the change in capacitance in order to solve for the differential force element. This differential force element will be the smallest amount of change in force that our circuit can detect with respect to the limitation of our circuit and the tools that we are using. Moving on to the calculations, we first take the derivative of our time constant with respect to the force applied. This equation will be the same as the derivative of our capacitance with respect to the force applied with an additional constant, which is the resistance seen by the capacitor. We can then rearrange our equation and solve for our differential force element. When analyzing the equation, we see two aspects to note. First, the minimum amount of force that can be measured will depend on the amount of force that is being applied. This inherently makes sense as the minimum amount of force that we can measure will depend on our capacitance, which will change as we apply force to our apparatus. Next, the minimum amount of force that we can detect will be negative. While this seems odd at first, recall Hooke's law that states that the force from a spring will be the negative of the spring constant multiplied by the distance the spring is stretched. Our next step would be to plug in the assigned parameters that were decided upon earlier into our equation. Note that these values are destined to change with respect to the application of our sensor. First and most importantly, the Arduino Uno sampling rate is 9600 Hz. This is the rate at which the analog signals get converted to digital signals. This would be our differential time constant element, as this is the smallest change in time that we can detect with our tools. Next, the radius of our plates are 2.5 centimeters. Our minimum separation distance of plates is 0.25 millimeters, and our spring constant is 100,000 newtons per meters. We then plug this in and simplify our equation to get our overall resultant equation for the differential force element for our specific set of parameters. When graphing this equation, we see that the minimum force that we can detect will increase with the force that is being applied. Thus, our circuit is more sensitive at lower force values and less sensitive at higher force values. This makes sense as the change in capacitance decreases with the amount of force applied. When solving for our differential force element, we are effectively taking the inverse of the derivative of the capacitance, which would mean that our differential force element should increase with the amount of force applied. Lastly, we like to go over some issues that we've identified with our current setup for application purposes. Firstly, the main issue that we've identified is the size of our setup. We wish to keep the size as small as possible to allow our sensor to be used for a wide array of applications. However, we run into many design and practical issues in doing so. The first issue is that obtaining reliable springs with the desired length and strength would be extremely difficult, even taking into account our parallel spring setup. This also causes issues with scalability, as the higher the force, the higher the spring constant would have to be, which would make obtaining springs even more difficult. The small size also makes the capacitance values very difficult to reliably detect and measure. These issues can be remedied in part by increasing the size of the overall apparatus and scaling the size with respect to the application in mind. The next issue is with our overall circuit or capacitor setup. Once again, due to the small capacitance value that we obtain, reliably detecting the time taken to charge and hence the capacitance is difficult with respect to the current circuit setup. A possible remedy would be to use some sort of elastic dielectric material, which would have a relative permittivity much greater than 1. This would increase the capacitance, making it easier to detect overall.